Good morning. Today we're going to talk about a new topic called analysis of algorithms. We'll see what analysis of algorithms is all about. And it's primarily about the efficiency of programs. How efficient is a program that runs? First thing that you must remember that is that whenever we use a computer to solve a problem, we're using it primarily because it can solve large problems. Okay, what do I mean by this? Let's say I want to find the sum of 5 numbers. Maybe I can just do it manually. Then if it becomes 1,000 numbers, 2,000 numbers, and so on, then you might want to use a computer to solve it for you. Okay, even if you know arithmetic progression or whatever it may be. So solving a problem can have on the computer can have many solutions. Okay, and what we require, a good solution, quote unquote. What do you mean by a good solution? Okay, and good solution means we need a means we want a an algorithm that is good. Okay, and clearly when we look at different aspects of an algorithm, let me call it algorithm properties, then we may have qualitative and quantitative aspects. What do we mean by this? We will see in a minute. We already talked about this in the standard for C code. If any of you have seen it, it talks about the aesthetics of the program. It should be elegant, readable, and so on. Okay, and whereas when you're talking about quantitative aspects, we want something that is economical in the use of computer resources. Okay, computer and human resources, because suppose I want to go back and modify the program, it should require much less effort. Okay, so what we'll do is we'll quickly do away with the qualitative aspects, because what we are going to look at is the quantitative aspects. So you may want a solution that is simple, at the same time generalizable. What do I mean by that? Let's say you're finding whether a given number is prime or not. It should not work only for numbers between 2 and 1,000, but you may want it to work for any number. That's the meaning of generalizability. It should be easily understood by others. Surely, in this course, your programs must be well understood by your TA, and So it has to be clean. You have to have a clear and clean implementation, and and surely not some tricky and archaic solutions. Okay? We don't want this. And it must be easy to modify. And you must write the correct program should be correct given the pre and post conditions which we studied about. Pre and post conditions. See, the point is, it's if you have your program, for example, is not going to work for all kinds of things, but as long as you're very conscious that it will work only for this kind of input and it will produce this output if the input is within this range, that's perfectly fine. Okay. And another very important aspect is that it has to be well documented. That is why I put up a sample of C code to show how documentation should be done. This is very important. Most IDEs today or integrated development environments do provide some way of doing a little bit of automatic documentation. Program must be modular, so that modular means it's divided into sub-problems. And what does this enable us? Easy evaluation of correctness, as we saw earlier. Okay, and makes it a lot more, and you can check at every level of every sub-problem level. This is very important. And generally, we also talk about something else called the ripple effect. A program is divided into modules. A change in one module should not have cause a change or cause an effect in the other modules. This is also very important. And most importantly, I will always advise you, now that you know, should not have flat code. We already insisted on the last assignment that every program must have functions, no flat code. We will soon see that we will divide responsibilities based on properties of the program, and we'll put functions in different files and see how we can compile all of them together, okay, and make one single program that works. Most importantly, this is a very important aspect. Remember, a program that you write that you design is your property, and you should be proud of this effort. Do not share. Okay, this is very important. There will be penalties in the course. Mostly zero. has already been stated in the evaluation. Okay, so we talked about the qualitative aspects. Let's look at the quantitative aspects of an algorithm. And basically quantitative. And here we are going to worry about the computational complexity. And we'll see how we are going to define this. Okay. What is computational complexity? It's the characteristics. It's characterized by the performance of the algorithm as the input size increases. Okay. And we'll see how we can quantify this. Give you an example. Suppose processing 100 elements takes n time, then if processing 200 elements takes 2n time, then we state that the algorithm is linearly dependent on n. Okay, and generally the pattern can be quite different. There are various patterns that you can see, and for example, you can have log n, which is less than or sublinear, and there is 2 to the power of n, which is exponential. Okay, much greater than linear. Okay, less than linear here. And you may wonder, no, what's the big deal about exponential or linear? Let's look at this. Let's say n is 100. Then if I take the roof of log of n to the base 2, this is going to be 7. And if on the other hand, I take 2 to the power of 100, this becomes very high. Even something like 2 to the power of 10 is 1024. And if you look at the growth rate of this and the growth rate of this is very much large. 1024 becomes, even for small size inputs, if I take n equal to 4, for example, n equal to 10, I'm going to get log of n to the base 2 is equal to 4, and 1024 is much, much larger than 4. So this is something that we have to worry about. So what we need is, if the problem is small, it really does not matter. But if the problem becomes larger, then exponential is a serious cost for us in terms of behavior. So what we would like is, generally, when we work with algorithms, we'd like to work with linear or at most polynomial. So we need some basic foundation, this, and we will get into the details in a little while. Okay? Some mathematical foundation is there, and we will discuss this. But I just want to, before that, go through a little bit of pictures, pictures. When we talk about the efficiency of an algorithm, here is an example. Let's say I want to find the maximum element in an array and also find its position. Okay. Version 1 of the algorithm may look something like this. P, let's say, holds the position of the maximum element. And let's say the array goes from A of 1 up to A of n. And for I equal to 2 to n, I may do something like this. If A of I if A of I is greater than A of P, then P is assigned the value of I, end of for, and I might say that max is assigned the value of A of P. This is version 1 of the algorithm. Let us look at another version. I could write P is assigned the value of 1, max is assigned the value of A of 1, and for I equals 2 to, going from 2 to n, do if A of I is greater than max, then P is assigned the value of I, max is assigned the value of A of I, and if, and end for. Okay, so there are two different versions of the program. Question is, which one is more efficient and why? Okay, which one would be preferred? So the question is, which is the algorithm that we will prefer? If you look at this program, it looks as if it has a fewer number of statements. This one is requiring an extra variable that needs to be declared, called max. Of course, both of them, oh, here also there's a variable max which is being defined. And but we would prefer this program rather than this for the simple reason. When you look at this particular statement over here, actually, if you look at, because we're storing the value of this, if this, we are storing the value of the maximum at any point in the variable max, here, for example, I need an access for the index, and I need another access for A of I, an access for P, and an access for A of P. Here, on the other hand, it's going to reduce one access for me when I'm searching for a particular element. And at the same time, if you look at it, this program is a lot more elegant and clear about what exactly we are computing. Okay. So we require more accesses here. This requires few more statements, perhaps, for example, max equal to A of I, extra assignment statement that we have here. This assignment statement is run only once, whereas in this, it's repeated whenever the value is greater. But this will be preferred because it is requires fewer accesses to memory, and it is also clean, elegant. Okay, so this is something that we will remember. Now, let's take one more example. Third example. Let's say I'm looking at today's attendance, and I'm looking at the various people who are there in the class. And, if you look at the Zoom, it gives you in terms of names. Maybe I would like. On the other hand, if it was sorted in terms of roll number, I want to see some X is present or not. Then if you want to check whether the X is present or not, and I have a list of roll numbers in the Zoom class today, then one way of checking this would be, while roll number not equal to the expected roll number, this is the person that I'm looking for, then do something end while and go on until it's possible that the person never came to class and won't be there. Alternatively, if I have the roll numbers sorted, then all that I need to do is, while roll number less than expected roll number, process, do some processing of attendance if I want to do. So what happens is, in this particular case, as soon as you've crossed, suppose roll number is a variable that's being incremented, goes to the next roll number or whatever. If the information is available in sorted order, then what we could do is we can reduce the amount of computation that is required. There are two types of complexities. We are primarily going to focus on time complexity, and I will talk about a little bit about space complexity too. What we mean by that is, how much memory is it going to occupy to run the programs. Time complexity is still considered very, very important, because it's going to give, given the size of the input n, how much time it is going to take to run the problem. Space complexity, we're saying how much memory is going to be required to solve the problem. Sometimes both will work kind of in tandem, where if I use a little bit of space, then I can reduce the time complexity, as in this particular example. What we did was we used this variable max to hold a of I here, and then we find that we require a little bit less time compared to the other program. Okay, so this is the important point about complexity analysis, and then in the we will stop here, and I will take the next part of the course, next part of today's topic. And